Welcome to the lecture on physical modeling of isothermal and non-isothermal system. So, we talked about the Reynolds as well as the Froude similarity, and in this class we will talk about the aspects of physical modeling when we talk about the isothermal as well as the non-isothermal system. So, when we do the aqueous modeling, so we will also discuss about it in our later classes. So, in that case we take the water as the common fluid, and if you talk about the modeling, so it can be done either in an isothermal manner, or you have to take even the thermal considerations. So, in that case the thermal similarity has to be kept in mind. So, how which type of dimensionless numbers are going to come in these cases. So, in this lecture we are going to have the brief discussion about those aspects. So, as we know that you may have the counter with the either the isothermal system or the non-isothermal system. Isothermal system means when we are not taking into account the temperature difference, we are just ignoring the effect of the buoyancy forces, or we are ignoring the effect of any kind of temperature gradient in the melt. So, that kind of system is basically the isothermal system. And in these cases the importance and validity of Reynolds and Froude modeling criteria can be examined by considering the relevant forces acting in Tundis model system with isothermal flow. So, basically you will have to examine these Reynolds as well as the Froude modeling criteria. So, as you know that the forces which are normally taken into consideration in these cases are the inertial forces, viscous forces and the gravitational forces. So, we know that we are basically also certainly must be knowing about these role of these forces. So, if you talk about the inertial force, so they give rise to the convective flow or the convective momentum transfer. So, basically these things take place because of the inertial forces. Then you have the viscous force. So, viscous force will lead to the viscous or diffusive momentum transfer. So, that is how these viscous force role becomes. Now, what happens that you may have either the laminar flow or maybe the turbulent flow. So, as you know that in the laminar flow the molecular viscosity of the fluid causes the exchange between the adjacent fluid layers and result in the diffusive momentum transfer. So, that is what the trait of the laminar flow is, and in that you talk about the molecular viscosity also. So, that comes into picture in the case of laminar flow. Whereas, in the case of turbulent flows, if you recall, then here the diffusive momentum transfer is not only because of the molecular at the molecular level or exchange of the molecules, but it will be also because of the exchange of eddies. So, eddies are of different length, and they are exchanging that over the relatively large distances known as the eddy lengths. So, that basically is of very large value. So, that is what is happening in the case of the turbulent flows. So, in the turbulent flow the diffusive momentum transfer depends upon the effective viscosity and not on the molecular viscosity. So, basically what happens that when we talk about the effective viscosity, so it will be nothing but the summation of the molecular viscosity and the turbulent viscosity. So, the diffusive momentum transfer which will be calculated, it will be basically based on these both these factors, like you have molecular viscosity as well as the turbulent viscosity, and both taking into account. So, the Reynolds number similarity is very important in the laminar flows, but becomes less important in the turbulent flow modeling, because as you know that in that case the molecular viscosity which is there. So, that that is not only the sole criteria for having the determination of the parameters, like for the calculation of the momentum transfer or so. So, in that case it becomes less important in the case of the turbulent flow. So, Froude number is important where both inertial and gravitational forces are acting on the fluid. So, if you look at the other number, the Froude number. So, in that we know that it is a ratio of inertial to gravity force, gravitational force, gravity force. So, in that you have this is becoming important when both these forces are acting on the liquid. So, that time your Froude number becomes important, and it becomes important in those cases, especially its use is there in the case of inclusion flotation, because in the case of inclusion flotation the particle shape which we take it, and the particle which is there inside the melt. So, that is that will be subjected to these forces, and they will try to coalesce, or they may try to float. So, this Froude number, that this Froude number similarity, that is to be taken into account when you have both inertial as well as the gravitational forces are acting, and mostly they are useful when we talk about the inclusion flow modeling. So, if you talk about the momentum balance equation, if you recall. So, your momentum balance for the turbulent flow in the Tundis, because in the Tundis normally the flow is considered to be turbulent itself. So, your momentum balance equation will be it will be like rho Vi Vj upon rho xj. So, this is your steady state momentum balance equation. So, it takes this form. So, you will have the pressure term. So, you will have dou p by dou xi, and then your term comes these convective terms. So, that it will be your dou by dou xj, and then you have if you talk about the turbulent flow situation, in that case you will have the effective viscosity coming to picture in place of the molecular viscosity, and then you have the term, that is dou Vi by dou xj plus dou Vj upon dou xi. So, that is how your momentum balance equation for the turbulent flow looks like. And if you try to analyze this, if you go for the dimensionless form of this equation, then it will yield the dimensionless number, and that will be in the laminar case you are getting the Reynolds number, and in the case of the turbulent flow you have the origination of the turbulent Reynolds number, and that is denoted by Reynolds number T. So, that is your turbulent Reynolds number that is found, and it becomes rho VL upon eta effective. So, that is how this number, this dimensionless number, number is defined, and for for having for maintaining that similarity between two Dundices which have the turbulent flows. So, you will have to see that there must be similarity. Each term in the dimensionless form should have the same value in both the systems. So, in the model as well as in the actual system, each term must be same, and it is assumed that when you are talking about that kind of system, in that case, apart from the geometric similarity, your turbulent Reynolds number also should be same. So, that has been found by many authors. It has been there has been modeling studies, water modeling studies carried out by many researchers, especially by Sahai and Emi. And then apart from that, there are many researchers who have worked on this, and they have found it that this Reynolds number, turbulent Reynolds number, that also should be the similarity in this in the value of the turbulent Reynolds number should also be maintained. Coming to the non-isothermal system. So, in most of the cases, the system becomes non-isothermal because the temperature cannot be said to be uniform. So, in actual practice, the system is non-isothermal because the temperature is varying. So, in actual continuous casting practice, the melt flow conditions may become non-isothermal because of many reasons like heat losses. So, heat loss may take place either from the top surface or from the walls. So, there may be heat loss from these places. So, that will lead to the change in the temperature. So, the situation cannot be said to be completely an isothermal case. So, then other cases may be like temperature of the inlet stream into the Tundis, it is different from the ladle. So, whatever is entering, so that is different from that ladle. So, that or there may be the temperature variation at the Tundis inlet stream and at some of the corners inside the Tundis. So, because of these temperature differences, the buoyancy comes into picture, and it has been seen that when such is the case. So, when we talk about the such cases, in that case the non-isothermal aspects are to be taken into account. So, you will have to see that you will have the different kind of dimensionless groups will be coming, whose considerations will be there for having the similarity analysis. So, so it would be useful if water modeling could account for the non-isothermal aspects of fluid flow phenomena. So, you will have to have the considerations of these non-isothermal behaviors which remains in practice. So, if you go to the non-isothermal system, so in that case, if you talk about the momentum balance equation. So, the momentum balance equation for the turbulent non-isothermal flow your momentum balance equation will go like this. So, it will be dou by dou t of rho v I plus you have dou by dou x j of rho v I v j, and then that will be equal to dou by dou x j of eta effective, that is your effective viscosity is coming to picture in place of molecular viscosity in case of turbulent flow. Then you have dou v I upon dou x j plus dou v j upon dou x I. So, and then you have the pressure term, that is dou P by dou xi, and in here you will have another term is coming because of the difference in the density. So, it will be rho minus rho reference, and it is multiplied by the G I. So, this is taking that buoyancy force into account. So, this term is basically taken into account for the buoyancy force per unit volume. So, now this is because of the difference in the density which is arising throughout the fluid body. So, that is why it is coming. Now, if you take the beta as the coefficient of thermal expansion. So, in that case, so if beta is coefficient of thermal expansion of the fluid, now in that case you can write that beta is nothing but minus 1 by rho reference, and it will be dou rho by dou T at pressure. So, at constant pressure. So, this is how the beta is defined. So, if you take a very small variation in, if you take that density variation to be very small, so that will be rho minus rho reference. So, in that case this rho minus rho reference will be beta into rho reference into then this will be delta T. So, for a small variation in density, you can write that this rho minus rho reference, that is dou rho. So, that will be equal to minus of beta into rho reference, and then you will have delta T. So, rho reference is the reference density, and in that case this Navier-Stokes equation can be further rewritten. So, your rho minus rho reference is defined as minus of beta rho reference and delta T. So, that term will come here. So, if you go to the to this Navier-Stokes equation, so that can be further written as dou by dou T of rho V I plus you have dou by dou x j of rho V I V j, and that will be equal to dou by dou x j of eta effective, and then you will have dou V I by dou x j plus dou V j upon dou x I, and then you have the pressure term dou P by dou x I, and then you have this rho minus rho reference, that term has come. So, that will be rho and reference into beta into delta T, and then you have G I. So, this term is coming once you have the buoyancy which is there in the case of turbulent flow when you are taking the non-isothermal conditions. Now, if you talk about the when we talk about the non-isothermal conditions, then we also talk about the conservation of energy equation. So, your equation for conservation of energy, so that will have its own form, and it will be like dou of rho Cpt upon dou of T, and then you will have dou of rho Cp T V j upon dou of x j. So, that will be equal to dou by dou x j, and you will have k effective and dou T by dou x j. So, if you look at these terms, so you will have k effective is nothing but the effective thermal conductivity which is there in the case of the turbulent flow. So, in the case of turbulent flow, you will have the effective thermal conductivity, that will be because of molecular as well as the turbulent part. So, that is how these it will be the summation of the molecular and the turbulent thermal conductivities. So, these together they will be governing these flow dynamics in the system. So, and also you will have the temperature at the inlets, you will have boundary conditions at the inlet. So, if you talk about the boundary condition at inlet, so it will be T will be T inlet. So, it will be the ladle stream temperature. Now, if you talk about this equation, and if this equation is we try to write in the case of in a non-dimensional form. So, you will have the non-dimensional forms like rho v star, rho star, v star. So, you are non-dimensionalizing it, every term is non-dimensionalized. So, if you non-dimensionalize this Navier-Stokes equation, so non-dimensionalizing, what you get is you will be getting these terms like you will have dou of rho star, then you will have Vi star upon dou t, plus you will have next term is dou by dou xj star. So, you will have rho star, Vi star and Vj star. So, these are the non-dimensional terms. Then that will be equal to dou by dou xj star. So, you will have this is effective viscosity, and that will be divided by rho reference, and this will be VL. So, that is coming from this side. So, that rho reference VL will be coming to this side. So, this is beta reference that effective viscosity divided by rho reference VL. So, this is nothing but the Reynolds term that will be coming here, and then you have dou of Vi star upon dou of xj star plus dou of Vj star upon dou of xi star. So, that is non-dimensionalizing these terms. So, and then you will have dou p star upon dou x I star. So, that is the non-dimensionalizing these terms, and then what you see is that your term which remains here, that will be beta delta T L upon V square into G I. So, this is the when you write this equation in the non-dimensional form, then this comes into this shape, and if you write the non-dimensional form of the thermal energy conservation equation, that can further be written as dou of rho star T star upon dou T, that is star, plus dou of rho star T star and then Vj star, and this will be divided by dou of xj star. So, that will be dou of dou xj. So, it will be K effective by rho reference and Cp and VL. So, that Cp is coming from this side. So, that will be Cp into VL, and you will have dou T star upon dou xj star. So, your these terms are coming, and in that case you will have these non-dimensional number which is defined here, and your non-dimensional temperature which is defined T star. So, that is defined by T minus T naught by T inlet minus T naught. So, it will be T minus T naught by delta T naught. So, this is how you are having the definition, and this is how you are getting those forms. Now, what you see this term, if you refer to this term, what you see from here, you are finding certain dimensionless groups. Now, that dimensionless group which is coming up, that one is 1 by Reynolds, turbulent Reynolds number, and that is becoming eta effective divided by rho reference VL. That is what is you are getting, eta effective by rho reference VL. So, this number you are getting, and this is nothing but the inverse of the turbulent Reynolds number. Then next is you are getting the one number which is defined as the Richardson number. This is coming from here. This is this number which is coming. This is known as the Richardson number, which is because of the buoyancy. So, we will talk about how this is defined. So, this is nothing but beta, then you have delta T naught, then you have L and Gi divided by V square. And one more number which is coming here. So, if you look at this, this is nothing but the inverse of the product of the turbulent Prandtl number and turbulent Reynolds number. So, this is nothing but 1 by Prandtl number, turbulent Prandtl number and turbulent Reynolds number. So, this comes as, so this is this term, this is K effective upon rho effective. So, you will have K effective upon rho reference, and you have Cp into V into L. So, what you see is that Cp by K. So, K mu comes like that. So, so that is your Prandtl. So, this is this is the inverse of this product of these two numbers, that is turbulent Prandtl number and the turbulent Reynolds number. So, these are the dimensionless groups which are coming when we talk about the non-isothermal system, and they need to be constant, and it is coming when we talk when we derive these thermal energy balance equation. So, already we have seen that the Reynolds similarity has to be there. So, and if you see that if the Prandtl number is assumed to be constant, in that case that similarity is also maintained. So, that is also satisfied. The only number which needs to be satisfied is the this number Tu, that is Richardson number. Now, if you look at this number, so it is nothing but it can be related to somewhere, it is related to the Froude number. So, Froude number is V square up this. So, if you take this term, so you have only this term extra. So, basically it has certain similarity with the Froude number. So, if you look at this number, so if you see this number is nothing but you can write it as Grasov by Reynolds square. So, this is this number is given that Richardson number, Richardson number. So, if it is nothing but it is coming as GL beta delta T naught divided by V square. So, it is nothing but the ratio of the buoyancy force, and that will be divided by the inertial force. So, this buoyancy force is resulting from the non-uniform temperature distribution inside the Tundis, and this basically causes the flow profiles to be changed many a times. So, it has been seen that because of this the flow profile in the Tundis will be changed as compared to what is being seen in the case of the isothermal system. And so, it is said that if this is satisfied, so this needs to be satisfied if the similarity has to be maintained. So, it can be concluded that if you maintain the constancy of these Richardson number, then the it means the ratio of the buoyancy force and the inertial force is satisfied. So, that will be of the two system will be same, the ratio of these two forces, and it will be satisfying the dynamic similarity of the model as well as the prototype. So, this when we talk about these non-isothermal system, this is there is another additional this type of one more dimensionless form, a number is coming into picture, that is your Richardson number. So, we can see its effect, how it affects. So, when we talk about the studies on the heat transfer studies inside the TUNDIS, then we will have a view of its effect. Thank you very much.